Chapter 6, The Cosmic Distance Ladder. The cosmic distance ladder is a set of techniques used in astronomy to measure distances between celestial objects. Because there is no direct way to measure great distances, astronomers rely on a series of indirect methods, each calibrated by more local and reliable measurements. These methods build on one another to extend reach from nearby stars to the most distant galaxies. The most direct method of determining distances is through the use of parallax. If you hold a finger up at arm's length, you can observe the visual effect that the parallax creates by closing one eye at a time, noting the shift in visual perspective as you do. Parallax also occurs in celestial objects, providing a measurable method for comparing two distances. As the Earth orbits, nearby stars appear to shift against the background of more distant stars. Because we know the Earth's orbital diameter, we can use the apparent shift in perspective to determine the distance to the star. Unfortunately, parallax is only reliable for a few thousand light years. For distances beyond the reach of parallax, astronomers use stars with a known luminosity. These standard candles are most commonly Cepheid variable stars and Type 1a supernovae. Cepheids have a well-established period luminosity relation, allowing their distance to be inferred from their pulsation rate. Type 1a supernovae are used at greater distances because they reach a consistent peak luminosity, which is handy for calibrating the Hubble constant. The Tully-Fisher relation uses an empirical connection between the luminosity of a spiral galaxy and its rotational velocity. The frequency of starlight is measured in various locations within the galaxy and then used to determine the galaxy's rotational velocity. After that, the intrinsic luminosity can be determined, which is compared to the object's observed brightness from Earth. This method is appropriate for galaxies out to several hundred megaparsecs. For elliptical galaxies, the smoothness of their light provides a way to estimate the distance. Nearby galaxies show noticeable fluctuations due to individual stars, while more distant galaxies appear smoother. This technique works well for intermediate distances, but is less common. Angular diameter distance. One of the more confusing tools for determining distances is the use of angular diameter distance, ADD, which measures how large an object appears in the sky. If you imagine the night sky as a screen, the angular size of an object would represent the number of pixels it takes up on the overall screen. Obviously, closer objects appear larger because they occupy a greater number of pixels on the screen. However, ADD changes that relationship at certain distances. At low redshift distances, objects appear to be smaller the further away they are. The weird thing is that at some point, the ADD effect flips, and the objects appear larger the further away they are. At the largest scales, distance is estimated from redshift using the Hubble-Lemaitre law. V equals the Hubble constant times the distance. This method assumes a cosmological model, typically the lambda CDM model, to relate redshift to distance via the universe's expansion history. Revisiting the distance ladder for static cosmology. All of the tools above remain relevant within a static cosmological model, with the understanding that the interpretations of ADD and Hubble's law require some adjusting. Fortunately, both of these methods are easily understood without invoking expansion or dark magic. In August 1997, 2 studies appeared on the archive equating ADD and gravitational lensing. Both were submitted within weeks of each other and independently reached similar conclusions, but used different techniques. Wald and Binney demonstrated how the angular diameter distance redshift relation can be equated to gravitational lensing from lumpy structures. This is a remarkable development that has largely gone unnoticed by the public. Virtually all literature still describes the ADD redshift relation as a product of the Big Bang. It took me a while to comprehend what was really going on. The ADD redshift relation doesn't make sense with any framework. The gravitational lensing explanation didn't make sense to me because of the models they used to obtain the result. The term inhomogeneous universe is particularly confusing in cosmology because it implies the interpretation is purely a novelty. All observations of stars can be considered to be an inhomogeneous universe. The inhomogeneity in Wald's paper refers to the distribution of mass along the null geodesics. It's not some alternate reality with a different cosmology. The ADD phenomenon is also present in the observations of mass objects, regardless of the cosmology involved. As we have demonstrated beyond a simple assertion, the Hubble redshift is more accurately understood as the result of a gravitational redshift due to the distribution of mass throughout the universe. The same geometry that eliminates the need for expansion for Hubble's law also eliminates the need for expansion as an explanation of the ADD redshift relation. In other words, the ADD redshift relation is a direct consequence of the distribution of mass. Light deflection from surface mass distribution. To verify that the mass distribution in this model produces the curvature required for gravitational lensing, consider the surface mass distribution. M of r equals 2k, or 2 times 0.833 kilograms per meter squared times pi times r squared. This corresponds to a uniform surface density. Sigma equals 1 over pi r squared times m of r equals 1.666 kilograms per meter squared. In general relativity, the deflection angle for a spherically symmetric mass distribution, the deflection angle at r equals 4g times 1.66 pi r squared divided by c squared r equals 4g times 1.66 pi divided by c squared times r. Thus, the bending angle grows linearly with radius, a hallmark of a constant surface density lens. This deflection leads to a geodesic deviation and angular magnification consistent with the statistical lensing found in sources 22 and 23. In particular, the presence of non-zero curvature and geodesic deviation confirms that this distribution can reproduce the same geometry required to cover the angular diameter distance through lensing alone, without invoking cosmic expansion. Everything circles back to the homogeneous assumption. It was devastating to cosmology. Homogeneity should be entirely banned as a concept in physics. It's not a real concept. It's not even a real concept in conceptual space.